Hello everyone, it's our honor to present our work Light-Dedup in USENIX ATC. And non-volatile memory NVM promises to be the next generation storage media due to its both memory and storage features. However, NVM is more expensive than existing SSD or HDD. For example, Intel Optane DC persistent memory costs 31 times more per GB than the Intel SSD. So, deduplication is a promising technique to enlarge the logical space and reduce amortize the cost. Here we introduce a basic workflow of deduplication file system. The first is we're going to introduce is inline deduplication. At first, applications will issue write syscall to persist the data. Then, deduplication file system will calculate the hash of that data as a fingerprint. Then, deduplication file system uses that fingerprint and the metadata table to determine if the data is redundant. If the data is truly redundant, deduplication file system just increments the data's reference count. Otherwise, it simply writes the data with reference count equals to 1. Here, during the step 3, there are two ways to calculate the fingerprint. One is to use non-cryptographic hash, such as XX hash, which is not safe and need further content comparison. But it can perform very lightweight calculation. The other is to use crypto hash function such as SHA-256, which is safe but is computational inefficiency. Besides inline deduplication, offline deduplication is similar to inline deduplication, but it performs the deduplication in the background, which means the data must be written first. The emergence of the fast NVM changes the game of traditional deduplication. For example, existing works often use inline deduplication to timely eliminate redundancy and improve NVM's lifetime. And they intend to use non-crypto hash-based fingerprint with byte-by-byte content comparison to enable lightweight calculation, since fast NVM has altered the software and I/O bottlenecks. However, can we just using the non-crypto hash alone for NVM deduplication to fully exploit the benefits of NVM? To answer this question, we revisit the study related to Optane DC PMM, PCM, and other NVM devices. We summarize the 5 common features that could impact the NVM deduplication. And existing works mainly focus on leveraging the I/O asymmetry feature by using non-crypto hash with byte-by-byte content comparison. However, they fail to exploit or consider the remaining 4 NVM features. And how can these features affect NVM deduplication file system? And how can we exploit them? The goal of our work attempts to answer these questions, and we mainly focus on the 2 important components in deduplication file system, that is redundant identification and the management of deduplication metadata table. At first, we find that existing redundancy identification approaches fail to consider the I/O buffers and read latency, the problem. Specifically, we built a simple non-crypto hash-based file system based on NOVA, namely naive, and we write 2 identical 4 GB files to NOVA and naive. This table shows the first write results. During the first write, the results surprisingly shows that the naive incurs much less data write time compared to NOVA. And this is not magic, since NVM's write is asynchronous. And write latency can be hidden by fingerprint calculation, which enables NVM I/O and CPU computation parallelism. During the second write, we find that the content comparison time of naive is even slower than the write time of NOVA. This is because CPU has to wait for the uncached data to be loaded from the NVM, and which incurs the blocked rate, and this results in long read latency. Then, a simple idea occurs to us is that, can we achieve a synchronous read just like NVM write does to hide such high read latency? The first solution is to use memory prefetch instruction to manually hide the latency. Here, all the hardware prefetcher can be helped, but NVMe is slower than DRAM, while hardware prefetcher is designed for DRAM and only prefetching 2 lines ahead. We assume this is hardware prefetch is too conservative for NVMe to hide its read latency. So our first attempt is to prefetch more aggressively. That is, when content comparison starts, we issue prefetch instruction for every catch line of that data block. Thus, a total of 64 instructions should be issued for one block. However, the number of the prefetch instructions that can be handled concurrently by the CPU is limited, which might make most of prefetch instructions serialized, failing to fully exploit the parallelism. The good news is that NVMe has coarse access granularity. For example, Alpten DCPMM has a 256 byte access granularity. Thus, there are no need to issue 64 prefetch instructions at first, but only 16. Thus, we propose in-block prefetch, IBP, which first issues 16 256 bytes stride prefetch. Then, the remaining data can be automatically loaded by NVMe. After the stride prefetch, IBP further prefetches the remaining catch lines that reside in the NVMe read buffer. At this time, the prefetch speed can be much faster than directly load from the media. Compared with the aggressive method, IBP can exploit NVMe I/O parallelism better. However, IBP cannot fully exploit the parallelism of CPU computation and NVMe I/O. For example, fingerprint calculation is felt to be leveraged to hidden the read latency. And our question is how to make this fully parallel like NVMe write. To address the problem, we further propose a cross-block prefetch CBP. The key idea of CBP is to speculatively prefetch the to-be-compared data block. For example, assuming after we write in block A, B, C sequentially, the next time, if we write block A, and we can speculate that the next block is B. To achieve this, we can maintain a hint field in the metadata entry and to record the related information. And we do not review its detail in this talk. See our paper for more details. We now introduce our 3 explorations on cross-block prefetch. First, during the initialization, we can obtain the first hint, that is the next block is block B. By leveraging this hint, we first propose prefetch current technique, which is used to prefetch the hinted block before any calculation starts. Thus, calculation can be used to hide NVMe read latency. Then, in the case we have speculated that the to-be-compared block is block B, there is no need to calculate fingerprint anymore. Thus, we propose speculation, which skips the fingerprint calculation directly. Finally, to hide the remaining content comparison and other computation, we leverage the hint to more aggressively prefetch the next block C, immediately after the block B is prefetched. In this way, we fully achieved the parallelism. We evaluate the effectiveness of CBP, and the result shows that CBP calculation is fully parallel with NVMe I/O, since CBP's overall time is same as speculation's content comparison time. By combining IBP and CBP, we propose speculative prefetch techniques. Speculative prefetch can significantly improve content comparison performance. Further, we propose light redundant block identifier, this component, which is a non-crypto hash-based approach with speculative prefetch-based content comparison. Next, we examine existing deduplication metadata table. Deduplication metadata table is used to store the basic information of deduplication. such as the mappings between fingerprint to the written data block and some additional information, such as the hint in our LRBI. And there are two related questions about designing deduplication metadata table. The first is how to efficiently search the entry in that table, and the second is how to manage the layout of deduplication metadata table more NVM friendly. There are two existing approaches to answer these questions. The first is to use all-in-NVM design, which deploys a static hash table in NVM to achieve fast indexing, allocation, and free. The second is an entry-based design, which uses in-DRAM structures to quickly index while using free list to allocate and free the entry. However, our observations show that these methods both suffer severe metadata I/O amplification. The main reason for this is because these approaches fail to consider I/O amplification caused by random access of NVM. So, to address the problem, we propose Light-Met table. The key idea of LMT is to deploy an index in the DRAM to quickly search for the entry without interacting with NVM, while managing NVM metadata entries in a region granularity to maintain locality. For index, we select in-kernel our hash table as our index due to its resizable, maturity, and scalability. For our in-NVM layout, we construct a region-based layout. The layout, each region is in a blocked size and linked by a 8-byte pointer. The region can be reused if no less than half entries are freed or empty. Note that we do not perform garbage collection by consuming 1 times more space, but the space consumption is small. Then, how does LMT can maintain locality? We introduce two scenarios. For unique write, entries are allocated almost sequentially in a region. Thus, we achieve spatial locality. For duplicate write, entries are potentially accessed sequentially. For example, a copy command results in sequential deduplication metadata accesses. Here we show the effectiveness of LMT under an aged file system. We punch the holes in the file to emulate the aging workload. The result shows that the region layout of LMT can significantly reduce metadata I/O amplification. In a nutshell, combining both LRBI and LMT, we built Light-Dedup. Light-Dedup can perform efficient redundancy identification by using speculative prefetch-based content comparison while retain low metadata I/O amplification by deploying region-based layout. With Light-Dedup, we can exploit all the NVM features during the NVM deduplication. More details such as crash consistency and protobability can be found in our paper. We now evaluate Light-Dedup on the same kernel as Nova with a 256 GB Optane DCPMM. We first perform micro-benchmark by using FIO. For high concurrency workloads, thanks to non-crypto hash-based architecture, NVM's read-write asymmetry can be fully exploited to achieve high deduplication throughput. Under single thread, for block-based I/O, Light-Dedup is much faster than NVDedup, and IBP contributes up to more than 15% to Light-Dedup. However, CBP cannot work ideally across syscall. We believe this is because CPU load queue is flushed during the context switch. For continuous I/O, Light-Dedup outperforms Nova, and thanks to CBP, Light-Dedup achieves up to 128% faster than Light-Dedup without prefetch. We further evaluate 4 real-world scenarios. We build a trace player to replace the trace and which can batch the continuous data blocks. Under high concurrency workloads, similar to FIO, non-crypto hash-based method contributes a lot. Under the single thread, copy workload benefits from large continuous I/O, and CBP can work well. For replaying trace using blocked I/O, and the results are consistent with FIO workload. IBP contributes here. For replaying trace using batched I/O, CBP can work well. Interestingly, Light-Dedup performs best under Holmes trace. This is because Holmes trace has the best consecutive deduplication rate. In summary, this work attempts to use deduplication to reduce NVM's cost. However, we find that existing approaches fail to fully exploit NVM's I/O features. So we propose Light-Dedup to fully exploit them. Specifically, we introduce LRBI to combine non-corrupt hash and speculative prefetch-based content comparison to improve redundancy identification. And we further propose LMT to introduce a region-based layout and uses in-DRAM R-hash table to significantly reduce metadata I/O amplification. And the experimental results show that Light-Dedup gains significant speed up against state-of-the-art methods with a low metadata I/O amplification. Thanks, and any question?